Hello, Mr. Aaron, Mr. Ryan, you alright? Yeah? Yesterday we talked about this 0-1 knapsack. Yeah? 0-1 knapsack. Meaning that each item that you can pick at most once. Right? So there's one item for there's one the number, the quantity. The quantity for each item is one. You can pick it or you can skip it. But if you pick it, you can only pick one, right? So we use the dynamic programming, top-down dynamic programming, yeah? DFSIC. When we are picking the ice items and we have a remaining capacity C, right? Then you have two choices. If the remaining capacity is bigger or larger or equal than the weight of the current item, then you can choose to pick it, right? If it's smaller than the current weight, what happens? If the remaining capacity is less than the weight of the current item, can you pick it?
No.
No, because it's too heavy, right? Yeah, because for example, if your capacity is 10 and then the item is 20, you can't put the 20 into your bag, 10, right? But when it's bigger than the weight, then you can keep, you can try, we can try to pick it, yeah? When we pick it, we subtract the weight of the current item from the remaining capacity, and in the meantime, we added the values we get, okay? And then obviously for each item, we can skip it. But we can skip it, then we have still remaining capacity, yeah? And then the key point here is we use the cache to remember the values of the, how many values we need to remember? The n times c, n times c. So the time complexity is O and c, space complexity is O and c as well, right? So we are actually storing the values I times C, okay? So let's top down. We use the dynamic programming top down, recursion with the minimization, right? Alright? So in the bottom up, yeah? Bottom up. So we need to store these I times C values in an array, right? And then we can compute the values. We fill the tables basically. Look, in the bottom up, we fill the values, first row of values, and then we start filling the second row. Yeah, this is bottom up, yeah. In the top down, we want to calculate this value. And in order to calculate this value, with recursion, with minimization, it needs to retrieve a value of the previous row. And again, it will recursion. The recursion will bring us down to the value with the smaller I, right? I is the row, okay? Yeah? And how the computer remember the values? Cache. But if the bottom up, we use the I array, which has two-dimensional array, I times C, right? To remember the values. And then we start filling the values from the first row, right? After we fill the first row, we fill the second row, compute the second row, and compute the third row until we reach this. Yeah? dp n-1 capacity, yeah? Until we reach this value, okay? So let's do this bottom up, okay? Just remember the directions, yeah? Bottom up and top down. The time complexity for each, for both is the same, the time and space. But usually the recursion is slower than the bottom up. Yeah, usually, practically speaking, the bottom up approach is faster. Why is that? Because there's no recursion call. There's no function call. For us to call a recursion, right? We need to spend time overhead in calling the function recursion. Yeah. Okay, which is faster usually? Come on.
Recursion is normally slow.
Yeah, slow because there's a function call, right? There's a function call. So we have to push the function call. There's a stack. We have to push the calls into the stack, right? That's usually slower than us proactively. What you doing? Proactively storing the values in the array. Okay. Okay, so. Let's just review the problem again, okay? So we have a few items, values. The weight is a WI, yeah, is a list of the weights, yeah, weights like 1, 2, 3, okay? And the values I is the values we can get like 1, 5, 3, okay? Right? And then PI, remember this PI is the value of 0, 1 selection, meaning that 0 we don't pick it, 1 we pick it, right? 0, 1 knapsack, 0, 1 knapsack, right? So we have also the capacity like something like 5, the knapsack, right? So what are we trying to maximize here? We are trying to maximize. The goal is to what? The maximize. Let's try to maximize what? We want to sum up. This is the sum, right? I equals 0 to n minus 1. N equals the number of the item, yeah, which is 3, yeah, 3 items. The size of these are the same, okay? Items. Eric, what did I just say? What's n?
N is the items.
Number of
Size
items.
the
The numbers, right? Okay, so we try, look at the sum, we try to maximize I equals 0 to n minus 1. So the pi times vi, that's the value we are trying to get, yeah? Pi times vi, okay? Pi times vi, okay? And then we also want to make sure the total weight does not exceed the total capacity. So we are trying to do this. I equals 0 to n minus 1 pi times wi. This is the weight, okay? And also, pi belongs to 0 and 1. There's only 2 possible values. You don't pick it or we pick it. Yeah? Make sense? Do you understand? Can you read this mathematics equation to describe the problem? One knapsack. Do you understand? Eric, Ryan? Any questions? Come on. This is the good chance for you to understand. That's mathematics. What are we trying to do here? We're trying to maximize the pi times vi, the value. Look, this is the value, yeah? We times it, sums it together, yeah? Yeah, this is the value, total value we can get. Subject to, make sure the pi times wi added together does not exceed the total weight, yeah? And subject to this equals total weight, okay? Yeah, and each value, why this pi has only 2 values, 0, 1?
You can pick it and not pick it.
Which one is pick it? Which one is not pick it?
0 is not pick and pick it is 1.
Yeah. And we use this value. This is control, right? Look, when it's 0, 0 times anything doesn't matter, right? Look, when it's 0, 0 times wi is 0, right? Anything. So it means this item does not take up any capacity from the original one. But it's 1. It's 1. Now we need to add the value, yeah? For example, this one, the value 2 plus 3, yeah? Look, what's the pi times wi sums together? 0 times 1 plus 1 times 2 plus 1 times 3 equals 5. It's less than equal to 1. And what's the value? 5 times 1, look Eric, 1 times 0 plus 5 times 1 plus 3 times 1, which is 8. So the maximum is 8. Right? The weight is 5. Okay? Yeah? Makes sense? Okay, right? Okay? Okay, then let's do this the bottom up, okay? Let's do this bottom up. So with the bottom up, we need to store the values in array, right? So it's a 2-dimensional array. Remember, the yesterday we call this cache. Top-down dynamic programming, we have this DFS function I and C, right? So it has 2 dimensions, I and C. So we need to be able to store these values, the combination of these values, yeah, into an array, okay? Let's say define knapsack 0, 1, and then we have what? Values, we have the weight, and we have the capacity, okay? Capacity. Okay? Yeah, capacity. So let's say dp equal, we need to allocate the 2-dimensional array. At the beginning, which is 0. For the second dimensional is capacity. So for underscore in range c plus 1, okay? Because we will need to be able to store the value up to c, including c, okay? And then the first dimensional is up to, for underscore in range up to n, okay? What's n? N will be the length of the values, right? The length of values, the number of items. It's also equal to the number of weights, okay? So now the first row, remember the first row, yeah? This is the first row. And then can you tell me what's the first row, okay? So this is the first item, okay? First item, the second item, third item, here n minus 1. The capacity, zero capacity. We want to pack nothing. When the bag has zero capacity, when the bag has one capacity, two capacity, etc. until C. Okay? So the first row we need to be for the recursion, top-down dynamic programming with the recursion, we can use the if. Remember, if C is smaller, if I is smaller than 0, we return 0, right? We can just do an if check. So that's easier, right? That's easier for us to implement. But for the bottom up, we need to tell the computer what values are those, these initial values. So dp, can you tell me what's dp0, the first row? dp0 C, what should we give to the values? When we are considering first row, and then we have the capacity. So we are only considering the first item, okay? This is the first item, yeah? And then we have a bag with the capacity C, okay? So what's the maximum value we can get? Come on. We have only one item, and we have a bag with the capacity C. So what maximum value can we get?
1.
1? No. You need, why is 1? Why is 1? Why is 0? Think about it. Okay, so this item has the value V0, okay? Has the weight W0. Yeah? I'm telling you, the item has the value 0, this value, this weight, and with this capacity C. So what's the value we can get? What should I put this in here? Come on. We need to first of all check which one is bigger, right? Yeah? This value, this weight. When this weight is smaller than C, what happens?
It's smaller than C.
When the item I'm trying to put in the bag is smaller, so that I can get this value, right? Yeah? But when this is bigger, when this is heavier, bigger than C, what happens?
You can't put it.
Then so what's the value here? We can't put it. What's the value we can get? If we don't put it, or there's only one item. Come on, there's one bag with C. And this item, when this weight is smaller than C, okay, we can put it, we get this value. But if we can't put it, when this value is bigger than C, we can't put it, what happens? What's the value?
0.
0, exactly. That's it.
0.
But that's two situations, remember? Yeah? That's two different cases. You need to tell me, right? Am I right? Does it make sense? Yeah? Yeah? Makes sense. Look, this value needs to be, if it's heavier than the bag, you can put it, that's 0. But if we can put it, that's the value we can get, right? Yeah? So we need to initialize this value, yeah, the first row. Okay, so we need to initialize the first row. For I in range capacity plus 1, right? Look, dp, the first row, the first item, and the capacity I equal, if it's 0, if what? If the weight, yeah, the weight, let's put an easy one, W. If the first item, the weight is bigger than I, right? Then we can put it, right? Else, and if we can put it, then that's V0, right? Do you understand this one? What are we doing here? What are we doing here? The whole thing here. What are we doing? Anybody? Everyone?
We are doing DP of the first row.
We want to put the computer first row, right? And first row is that we are considering the first item, right? And then if we can put it, then we put a VI, for example, yeah, VI here, yeah. If we can put it for V0 here, and if we can put it, if the way look at the C, W0 is bigger than I. If W0 is bigger than I, then bigger than I is increasing, yeah. If I is increasing, then I is increasing, the capacity increasing, then there will be 0, yeah, obviously, in the right? It could be 0 at the end. Look, if C is bigger, if the capacity C is smaller, look, if it's bigger than that, then it will be, here will be the value. Like most likely, okay, most likely. But if the capacity is smaller than the value, then this will be 0, right? Yeah, I'm just giving you some example. And after this, we fill in the first row. And then now, what should we do? After we fill in the first row, what should we do now?
Second row.
Second row until which row?
C.
Until n minus 1 row, because we have n items, right? So the first row will be for I in, we start from the second row, which is 1, second row, right? Up to n, the n row. And the second iteration will be for j in range, let's start to c plus 1, right? And then now I can fill each pixel, yeah? So each number in each row, in the I row. dpij equals max of what? dpij. Actually, do we need the dpij? We probably don't need it, okay? Let me write it first. dpij, and look, if we don't pick it, obviously will be j dpi minus 1, right? The previous item with still j complexity. If we can pick it, I minus 1, j minus the weight will be which item? I, right? And at the meantime, we have the value. Let's change this to value. Yeah, the value I, right? What's the sound? Okay, but look, the j needs to be bigger than wi, right? So I have to say if j bigger or equal than wi, else otherwise there'll be just 0. Okay, yeah. And then at the end we just return dp n minus 1 capacity c, right? Ij. Look, when we compute the dpij, we are only relying on I minus 1, the previous row, j and y. So we probably don't need to put a max here, right? We can just say dpij equals these max, obviously max of these two approaches. Okay, either we don't pick it, we still remaining j capacity, or we pick it j minus wi. Wi is the weight of the current item, j minus current item, right? But if we pick it, we get the value, the vi. Okay? Yeah? Yeah, if j bigger than wi, right? If j is smaller than wi, what does it mean? It means that the current weight, the item's current weight too much, yeah, has exceeded the capacity of j. Then in this case we can't pick it, then that's 0, right? Remember, this is quite similar to here, right? Yeah? Everyone, anybody? Alright?
Yeah.
What's the time complexity? Come on, it's an easy one.
Square. And n and c.
Oh, n times c, because we are just feeding the table, yeah? Rows by rows, column by columns, yeah? We're starting feeding here, one by one, yeah? The first row here, and then second row, and the third row. Yeah, we are trying to fill in the table, yeah? Yeah, we're trying to fill in the table. When we fill in this table, we need to rely on the previous one, this one. For example, we are calculating this here. We are calculating this cell here, yeah? So we need to compare this value, which we have computed, yeah? And then we need to go through the range j minus wi, could be somehow here, yeah? For example, if it's this one, then which one is bigger? And then I put it here. I store the value here, right? Yeah? And when I store this value here, the next row, yeah? The next row, when I calculate here, I also need to reference this one, right? And then the previous one, right? Make sense? Yeah? Okay, so to sum up, what have you learned so far today?
We learned about the 0, 1 knapsack.
Okay, what approach are we using today?
Doing the column thing.
What is it called?
It's called column thing.
So what approach is this? We are calculating from bottom to up. So what do we call it? Bottom up dynamic programming. Okay, what's dynamic programming? Come on.
Just remembering stuff.
remembering stuff. We're done. That remembering the values. Yeah, we're remembering the value. We're proactively storing the values in the array, right? That's the difference to the top-down dynamic programming, which we use just the magic keyword cache, right? We ask computer to cache it. Yeah, the top-down, we want to calculate this value. Yeah, okay, this is the key part. Come on, workers. Top-down dynamic programming. We want to calculate this value. We ask computer. Okay, then computer just do this top-down. Yeah, you could for each value, you will have a cache to remember. Yeah, it has this. It knows how to remember it once you calculate it. This is top-down. But for the bottom-up, we are constructing the table by ourselves proactively. Right, we're storing the values in the DP. Right, we compute the first row, we store the value in the table, and we use the first row to compute the second row, we use the second row to compute the third row, etc. until we reach the n-1 row, okay? The nth row, okay, the last row, okay? Yeah? Practically speaking, the top-down dynamic programming is easier to implement because for the boundary, yeah, for the boundary, if the weight is smaller than if the current capacity is smaller than the weight of the current item, then it returns 0. But so we have to say, okay, it's 0, right? Here, okay? So ideally, so to sum up, the top-down dynamic programming is what? It's easier to implement, yeah, because we're just making use of the cache, magic keyword cache, to ask computer to remember the value for us. Right, it's easier to implement. The top-bottom-up dynamic programming in a reverse way, yeah, we calculate the value in the reverse order. It's not so easy to implement, right? We have to construct the values arrays, two-dimensional arrays. We store the values in it, right? And then there's details that you might go wrong, right? Things might go wrong, right? But it's quicker, yeah. In terms of time and space complexity, both are the same, right? Because both are all computing the values, filling the values in the table, and each one is only calculated once, right? Either using cache or using the array. Make sense? Yeah? Okay, that's it for today. Bye-bye.
Bye.
Bye-bye.